morning, everyone. Thank you for being here at 9 in the morning. And I promise I will try to have some mercy of the theories and keeping the technical details to a minimum, but I'm happy to answer questions later about that. So, exotic decay modes, this is, I discovered a broad term. So this is my personal view on what I call an exotic decay mode, and I'm going to summarize basically our latest work in Warsaw by starting with a definition, or let's say, what is the physics playground? So what type of physics questions we are trying to answer? Briefly go through the experimental approaches that we are taking in order to answer these questions, and show you some selected recent results to conclude with a summary and an outlook on future studies, now that we can resume our experimental activity in particular. So, exotic nuclei, we focus our research mostly basically at the proton drip line and study light to medium nuclei. We had also a couple of studies, there's helium actually missing here, on the neutron-rich side, but I'm not going to talk about this today. So what we want to study is nuclear structure far from stability. This is actually the perfect audience for this. We look for new decay modes, but also some of this information can be also provide input for RP process calculations, as is in the case of zinc isotopes, for example. When it comes to light neutron-rich nuclei, we know already from yesterday's discussion that this is a very fertile playground, because you can have emission of beta-delayed charged particles, basically a zoo of light. The charged particles can be emitted, and they can allow to probe neutron halos. So this is kind of an obvious picture. It has been shown already. I had already great introductions over the last 2 days on this type of problems. I borrowed this from Bertram's and Maria's paper. So when we look at proton-rich nuclei, we have strong beta transitions. We have the isobaric analog state that usually falls within the Q window for beta-delayed charged particle emission. So it's unbound against the charged particles. We are beyond n equals z. So we can go basically, and we have low separation energies for 1, 2, 3 protons, alpha particles, etc. So we can go and study feeding of excited states in the daughter nucleus by doing a charged particle spectroscopy. On top of this, and this is in Warsaw has been for the last 20 years, it's actually 20 years since the publication of the discovery of 2 proton radioactivity by Bordeaux and Warsaw groups. We have also the phenomenon that Jerome already introduced yesterday of 2 proton radioactivity. And this 2 proton radioactivity is expected for even Z nuclei beyond the proton drip line. And in particular, okay, you can have sequential decay. This has been observed in some cases, but this is not as interesting as the true simultaneous emission that you have when the 1 proton channel is blocked because of Q values. I mean, yesterday it was already abundantly introduced. It was first predicted in the early 60s, actually in 1960. By Goldansky, so 60 plus years ago, observed for the first time in 2001 experiments, 2002 published, and then we moved on to look at the angular correlations. And this is the key question, the physics question, right? You observe 2 proton radioactivity, fantastic result. But what can we learn from it? We can learn about masses, nuclear forces, structure, because we are around shell closures. And we can learn about all these properties beyond the proton drip line by studying 2 proton radioactivity. Of course, you have competition in most cases with beta plus and electron capture decay. And the question is, what is the mechanism here? Is it sequential or is it simultaneous? Do we have diprotons independent on correlating protons? So the way to answer this, and I feel like I'm preaching a little bit to the choir here, is to go and look at the angular distribution of the two protons. You can see here predictions for iron 45 by Grigorienko. These predictions were made for the NSCL proposal back in 2007. So you can see here diproton prediction for angular correlations for diproton emission through three-body decay, and here you have the phase volume. So even if you don't have a great angular resolution, you can distinguish, if you have, let's say, sufficient statistics, you can distinguish at least between these two global pictures and then draw your conclusions. But we're not only focusing on two proton radioactivity, we're doing also charged particle spectroscopy. And here already some basic information like measurement of branching ratios and half-lives carry a lot of input. So for example, we can look at the competition between beta decay and particle capture, so that this information is useful for the shaping of the RP process path. If you have beta delayed proton emission in a sensitive significant amount, this can influence the amount of protons available during this explosive event. But also, and I find this extremely important, we can compare our experimental results with theory. Theory is essential, right? And we need theoretical inputs, especially, for example, for RP process calculations, but we need to validate this theory, because one thing is to test it close to stability, another one is to test it so far away where you start to have unbound systems. So we want also to validate and check theories in such exotic nuclear systems. And we do this with charged particle spectroscopy. Of course, you can do also beta delayed gamma spectroscopy for a less unbound state. But what the charged particle spectroscopy allows us to do is to investigate the structure of these exotic nuclei and probe the beta decay strength in the high energy end of the Q value, where charged particle emission dominates and wins against gamma emission. And you can also determine the width, gamma proton width for selected excited states. Also, when you have more than one proton emitted following beta decay, you can also look at angular correlations and try at least to figure out about the decay mechanism. This question was raised, for example, yesterday. It's not easy because these are small branching ratios usually, but it is possible. So our adventure, I call it an adventure personally, my interest in these topics was born 20 years ago when we discovered the two proton radioactivity from iron 45. You can see here the original spectrum, the Daniil data with nice narrow peak in silicon. This was silicon detectors experiment. So this is the total energy in the decay of iron 45, and this was our GSI measurement with 4 events observed, but 4 clean events. So these two experiments provided a good measurement for the total energy, because no TPC has the resolution of the silicon detectors, but the two protons were not resolved, right? So, and auxiliary detectors were used in order to prove that these were not beta delayed protons. There was like 90+% crystal around to veto gamma rays and see the two protons in anti-coincidence with 511 transitions. So the next step, this was kind of an obvious step, was to go towards time projection chambers, right? In order to do angular correlations and measure, reconstruct the momenta of the two protons emitted in the decay. So you can see here, this in both cases is the case of iron 45 in Bordeaux, and they developed classical TPC, I call it classical electronic readout type of detector. And they measured iron 45 at Ganin, while in Warsaw, an optical readout TPC was developed. There are advantages and drawbacks in each of the methods. You can see here, this picture was actually shown yesterday. This is one of the iron 45 ion stopped in the active volume of the gas, and the 2 protons emitted. And this is a sketch of the detector, but I show you in a moment just the general principles of how this detector works. And this is how it all started. So we do have, from the experimental point of view, our own challenges when we do this type of physics. First of all, you're dealing with very exotic nuclei, which means low production rates. The first iron 45 experiment was 1 ion per day. We had 6 ions in total, 4 of which decayed, 1 we missed, and 1 was beta delayed proton. So it's challenging. So the decay modes are rare by themselves. So you have small branching ratios on top of that. Normally you have high background levels. So from the physics point of view, we need to detect low energy particles and do particle correlation measurements. So how do we attack each of these points one by one? I usually go with the beam when I talk about this. So let's start with production of the isotopes of interest. Typically, but not exclusively, we use projectile fragmentation coupled with in-flight separation. And then we go to the lab, which gives us the best conditions for the dedicated physics case. So we actually we went to Mars at TAMU, to RIKEN, Dubna, FRS, and to the NSCL. So we take the beam. Usually typical energies are, let's say, about 50 MeV per nucleon, all the way to several hundreds of MeV per nucleon in RIKEN, for example. We impinge the beam on a target. We use typically fragment separator to try and select the ions of interest and separate them from the rest of the zoo of ions, more or less exotic, that are produced in the fragmentation reaction. And then we do ion by ion identification, which is crucial when you want to have proper correlation and to know who is your nuclear species that decayed in that particular way. And typically this is done by standard matrices, energy loss versus time of flight. And then our method of choice, as we figured out, is to implant these ions into the optical time projection chamber and look at their decays. And the optical time projection chamber, in brief, it's a gas, it's a volume immersed in a uniform electric field in which you stop your ion and then you wait for this ion to decay. Charged particles are then ionizing the gas. Electrons are emitted, drift towards the amplification stage, they are multiplied, and the light is emitted. And then we just take a picture, take the photomultiplier signal, feed it to a fast oscilloscope, typically 50 megahertz, and analyze this data. Of course, we record also auxiliary signals, like, for example, anything you need for particle identification, so that you can correlate your decay event with the ion that emitted it. Important, we stop the beam upon trigger, okay? So that we give it enough time to have no ions coming into the chamber while we are waiting for the decay. And then it's simply Pythagoras theorem. You have a 2D image with the projection of your track on the plane of the CCD camera. You have the time distribution of how fast the electrons reached your anode, which gives you the Z direction. If the proton points down, the Bragg peak electrons, so the most of the light, will arrive earlier. So this was actually a proton going upwards, and then you just reconstruct in 3D. Of course, the data analysis is more complex than that, but the principle is extremely simple. So first case I want to show you, this is an experiment we did just before pandemic at RIKEN. And the idea was, okay, let's study two proton correlations in zinc 54. So far, two proton correlations were studied only for iron 45, nickel 48 still has too little statistics. And so we said, okay, let's look at zinc 54. Here the question is, can we see the Z equal 28 shell closure in the proton-proton correlation? So this is again the picture from the iron 45 case to give an idea of what type of correlations we might expect. So we went to RIKEN, which we knew was the best place where to try and do this experiment. There was an experiment by the Bordeaux group that measured also cross sections in this region, just a little bit higher, the germanium isotopes experiment. So we knew that typically fragmentation of krypton 78 at 350 MeV per nucleon on a beryllium target should do the trick. They have 300 particle nanoampere of beam, which is enormous and actually difficult to take for the detectors. And ion by ion identification, we did apply selective triggering because our detector can take 1 Hertz. Okay, so we did have to kind of do selective triggering and stop the beam upon a good implantation. And this is what we got. So this is the total of the statistics we managed to collect in a couple of days of running. It turns out that despite our most pessimistic assumptions during proposal preparation, the cross-section is actually about 100 times smaller than this very conservative estimates. So we observed just a handful of ions, and then on the flight after 2 days, it was obvious we would not get 50 to 100 counts, which you need for a kind of sensible angular correlation measurement. So we turned this into, let's make something useful out of this. So we did look at the production cross sections for zinc isotopes, because it's obvious, everybody knows that APAX doesn't work for these isotopes, right? You can see here. So these are zinc collection from very recent publication by Adam, the student who is looking into this. You have germanium, selenium, and krypton from literature. We have zinc from our measurements at RIKEN here. So what you see here, the data points are experiments either from our current work or previous work at NSCL, and I think Bertrand's paper is from Ganil, right? And you can see the dashed line is APAX. The farther you go out, the lousier it gets. This is a well-known thing, that's why you assume conservative. But if you look at the zinc isotopes themselves, something was known here, okay? And yet there is a drop in the cross-section. I mean, this is log scale. Sorry for the online spot. I think this works best, right? So you have, even with pessimistic predictions, you do have a drop in the cross-section. So what we did was, okay, now we have numbers for RIKEN energies, okay? And this beam and target combination, of course. But let's look, and you can see here numbers, I don't know, it's probably too small. At APAX is about a factor of 50 higher cross-section. So we asked Oleg Tarasov to kind of look at his model, and he did calculations for us. He compared a lot of different input. He used a lot of different input masses for his semi-empirical model to estimate cross-sections, and we validated his model with this data. So this is what he calls AA model. And you can see that for all the zinc isotopes, it gets pretty close, let's say within a factor of 2. And his data, this is just 2 different masses. The one which performs best is the one with the Solling line using Hartree-Fock 22 mass formula. And for comparison, there is the mass, atomic mass evaluation formula. So this is becoming, at least for us, the way to predict cross sections and plan future experiments. For completeness, Adam is looking at the decay data. Sorry, now let me finish on this, because we compared also our cross-sections from Riken with Ganil, because the cross-section was known from Ganil experiment, but it's a nickel-58 beam on a nickel target. It's not pure fragmentation reaction. We know that the Ganil energy, this type of reactions work better for these isotopes. And the cross-section is indeed much larger for that reaction, but then you lose in luminosity. And at the end of the day, this is still a very, very challenging experiment. We also looked at predictions. What can we do? Which are the next 2 proton emitters on the basis of mass formulas, energy available, and probability of survival of the nucleus through a separator, for example. And the best candidates are still the germanium isotopes, but we know now that the germanium-59 does not decay by 2 proton emission. There is still a chance for germanium-58, but half-life is pretty short. So it might be challenging to have it flying through the separator and arriving to the detection setup, while the selenium isotopes seem to be too short-lived. So it's getting trickier and trickier.
I have a question.
Sure.
Maybe, may I ask it now?
For me, yes, if it's okay.
Probably you can. Yeah, okay. Probably you can. Is Olivier Sorlin asking question? Probably you can, even if you don't have that many events, you can sum these events with the ones of Ganil, and altogether have, I don't know, 20 or something. But my question was, are all the states, the events you found are 2 proton emitters, or they are beta delay 2 proton? Okay, you come.
I was coming to
okay,
this.
it's coming.
Yes.
It's becoming worse. Okay, I'm afraid.
So
okay.
We had some 15 ions identified at big reefs, and I don't know how familiar you are with big reefs, but we did the cross-section measurement. We did it at F7 focus, so we had their detector for identification, while our detector was positioned much more downstream from that at F11. So we realized that there was quite an important loss from F7 to F11. So of the about 15 ions that are in the ID plot I showed you before, only 5 made it to the were correctly implanted, because that's the other tricky business here, is the implantation range is broader than the thickness of our detector. As you can imagine, right? It's the same at least. So these are 2 of the events I chose. I admitted the 2 prettiest ones, and you can see the 2 protons. So 4 are fully reconstructed. Of course, later we should put together the data, because at this point we really have to join forces in order to get a global picture. And you can see the fit. I don't know if you can actually see it, but the fit here with the individual components on these are the photomultiplier signals. And this is the projection of the CCD signal. And the student Adam is who is finishing the data analysis here, so I cannot show you anything more, is also fitting in 2D by comparing to simulations. So this is as much as I can go for now for zinc 15. Recent case we did. Now I move to beta delayed multi-particle decays with some very exotic decay channels. We looked at the region around the silicon-22. We have 2 isotopes here that are interesting. They have very similar energy balances, silicon-22 and silicon-23, which were both known to decay by beta delayed 1 proton and 2 proton emission, mostly through the isobaric analog state. This is Ganil work from the mid to late 90s. But there are other open channels like beta delayed 3 protons, alpha proton or proton alpha emission, and even beta delayed helium 3. But none of these decay modes was observed so far. But as you can see, the Q values here are pretty large for the decays through the isobaric analog state. We performed an experiment. We went to Texas A&M at Mars, where we used the silicon-28 beam on a nickel target. Again, ion by ion identification. You can see here the identification matrix, selective triggering, and beam stopped upon good implantation. So the principle is always the same, or let's say 95% of the cases we work in this mode. We had what for us is a huge amount of statistics, at least for what we are used to in this type of experiments, about 7,500 implanted silicon-23 ions, 82% of which decay by beta delayed proton emission, and almost 8% by beta delayed 2 proton emission. And you can see here the spectrum, okay? So what you see here is the beta delayed single proton spectrum. So you have groups here. The shape of the spectrum is influenced by the fact that you can see here, we start to lose detection efficiency between 1 and 1.5 MeV proton energy, simply because the protons run out of the chamber and we cannot reconstruct the energy. A lot depends on the angle in which they go. But we have basically 100% efficiency below 1 MeV. Statistics here is limited, but there is one additional, I call it proton group. I cannot call it proton transition. It's actually these groups of counts are probably due to transitions through different states in the daughter itself. But okay, there is new group here. This was already observed into previous groups, and the improvement in the beta delayed 2 proton branch is most likely due to the fact that now we do see exactly the 2 protons emitted. So you have no ambiguity whether it's a higher energy single proton or 2 protons. But a nice, let's say not surprise, but result is that we did observe beta delayed 3 proton emission from silicon 23. So this is the first observation for this decay mode from silicon, and we got 2 events, one of which is shown here. I admit this is the prettiest because in the other events, one of the proton had higher energy and escaped the chamber, so we cannot have full reconstruction. So you have the ion coming, stopping more or less in the center of the chamber, and then the 3 protons are emitted all at once, about 7 at a time. This is absolute time scale with respect to the trigger. 10 to the 2 times, so this is what, 7.5 milliseconds after implantation. You see 1 proton, 2 proton, and the 3rd one. The branching ratio, we have 7,500 events, efficiency to take into account, also because our observation window is not infinite, right? So you have some few half-lives, which gives you more than 90% probability to see a decay. Branching ratio 3 times 10 to the minus 4. So this is typical for these decay modes. The energy, the total energy of the 3 protons, we cannot reconstruct individual energies, but the total energy of the 3 protons is about 3.6 MeV, which is compatible with the decay through the isobaric analog state. So, or some state nearby it. So no surprise there. For the other event, we could set a lower limit for the total energy of the 3 protons to be also, which is also compatible with decay through the isobaric analog state. But the pretty thing is that we did also see a much more exotic decay mode, which is beta delayed proton plus alpha decay of silicon-23 with 1 event. We call the identification tentative because the fit is not fantastic, but I'm pretty convinced that it is real. So you can see this analysis of the silicon's isotope has been done entirely by my student, Ola Chenmi, and she went through all the 2 proton events, okay, looking for cases which were compatible with having one of the particles being an alpha. You can see here this short track much brighter than the other one, so it's much higher energy loss. So the block formula tells us that this could easily be an alpha particle. Then she fit the event, assuming that the two particles were two protons and making the assumption that the shorter one is actually an alpha particle. And you can see here the results of her fit. So the R squared, the residuals are kind of compatible with each other, but the blue fit, which is alpha plus proton, is actually by eye telling us that this looks much more convincing. And also, if you look at it and you look, okay, with the alpha and proton option, you have a proton energy would be 1.6 MeV, alpha energy 1.2 MeV, and again, compatible with the decay through the isobaric analog state. Well, if you assume two protons, then they would have very different energy, but again, compatible with the decay from a state, now this time from a state below the isobaric analog state. Now, assuming under the understanding that these are proton and alpha events, we said, okay, which one comes first? Is this proton plus alpha or alpha plus proton? Well, we looked at barrier penetrability considerations under the assumption that you have an L equal 0 alpha. L equal 2, I don't believe, would make it out with such a low energy. And these favor that the option that the proton comes first and the alpha comes later. In literature, there are already a couple of cases known. In neon 17 and carbon 9, you have both decay paths observed, while in magnesium 21, it's the proton plus alpha path observed. Of course, all these experiments suffer from extremely low statistics, so you cannot exclude that the other decay path is actually there, simply not enough statistics to observe it. But the nice story here is that if you look at the known cases of proton plus alpha or alpha plus proton, they're all coming from TZ equal -3½ nuclei, which are neon 17, carbon 9, and magnesium 21. The other candidate is oxygen 13, which has a predicted branching ratio in the same order of magnitude 10 to the -4. And they all decay through alpha conjugate nuclei. The same is for oxygen 13. So Lund and collaborators looked at the systematic of beta-delayed multi-particle decays for isotopes with TZ equal -3½ or lower, and they came to the conclusion that the presence of these extremely rare decay modes like beta-delayed 3-proton emission or proton plus alpha emission are actually not due, like one might think at the beginning, to the fact that the decay proceeds through alpha conjugate, I'm almost done, alpha conjugate nuclei, but rather to odd-even effect. And they also concluded that the observation in nuclei with TZ equal -5½ like silicon 23, sulfur 27, and argon 31 would support this conclusion. So the discovery of this decay branch in silicon 23 in argon 31 has been known now for 10 years about, and the same from chromium 43. So the fact that this nuclei decay by beta-delayed 3-proton emission, and tentatively the observation of proton plus alpha delayed proton plus alpha emission in silicon 23 does support their conclusion. We looked also at sulfur 27. The data analysis is very preliminary, but so far we haven't seen any beta-delayed 3-proton convincing candidate for it, but never say never. As I mentioned in my introduction, one of the things, one of the goals also of these measurements is to validate theoretical calculations. In this region, now I'm still talking about the silicon region. The state of the art here is shell model, okay? They give a very accurate description of the low energy structure of aluminum 23 in this case. The calculations were done by Alex Brown in the late 90s. They were published in the Blanc et al. Paper. But what we did here was to use an alternative approach to validate a new model. So this alternative approach, the calculations were done by Wojtek Satua in Warsaw with the help of his postdoc. The alternative approach is multi-reference density functional rooted calculations when they extend the conventional Schmidt field by restoring angular momentum and properly treated isospin symmetry. So the goal here was not really to compete with shell model, but to validate this approach in a nucleus where actually there are very good benchmark shell model results, so that we could test the functional in this match region without any adjustments of its parameters. So this is what we found. So the configuration space and configuration mixing calculations use SVSO density independent scheme interaction. And the low energy spectrum, which is here at the bottom, compares relatively well with shell model. So it's not that bad. Problem is that the isobaric analog state is predicted about 2.5 MeV lower than experimental result and than the shell model. So this tells us that we need a better calibration of the symmetry, energy strength in the functional. Also, the Gamow-Teller decay to states below 3 MeV, so to these states, here gives matrix elements much smaller than 1, and this can be explained by shape difference for the silicon 23 ground state and aluminum 23, which gives the Gamow-Teller matrix elements hindrance, and isobaric analog state dominance in the decay pattern. Above 3 MeV, there is still work to be done. There is a much more important difference, which is still under investigation, and we require better calibration of the function. So this is a challenge for the theorists to keep up. To summarize, we use our optical time projection chamber in connection with different ion delivery systems. It's a simple and very efficient tool to search for rare decays and investigate charged particle decays obscured by beta background. We are blind to the beta background, and it can provide precise branching ratios for beta delayed charged particles channels. We can reconstruct low energies, well, although with worse resolution than with silicon detectors. Most recent results include the study of zinc 54 and beta delayed multi-particle decay channels of silicon 23. This is a beautiful example of carbon 9 decay by 1 proton and 2 alpha particles from a couple of years ago. And there are limitations to the method. We are very well aware of that. So if you have more than 2 particles, reconstruction is very difficult, if not impossible. We can handle maximum on a very good day 2 Hertz rates. Long half-life, like in the case of beryllium 11, are a nightmare. And of course, there is a limited range of measurable energies. We are bound by the volume of the detector and the thickness of the gas, because you need to stop your ion, you need to stop your protons, but at the same time, you want to measure also low energy protons, so you cannot make your gas too thick or your tracks will be too short. We have developed a new active target, TPC, with planar readout for nuclear astrophysics studies, but not only. So we are looking forward to using this one also in beta decay studies. And looking at the future, during pandemic, we actually sat down and started to think about the new proposals for new experiments. And so like Jérôme already anticipated, we are planning to measure titanium-39 in Ganil and look for its for its 2-proton decay. And we are waiting for a full beam intensity at F-rip in order to measure angular correlations in nickel, the decay of nickel 48. So please stay tuned. But to thank my collaborators. And Jérôme, can I have 30 seconds?
Sure. Sorry,
self-advertisement. We have 2 conferences coming up in Warsaw next year. One is Procon in June, downtown Warsaw at the main campus of the university. And after a break of one round, the Mazzocchi Lakes conference is also back, hopefully next year. Thank you.